Continuing our look at the quadratic function. So let's just draw up our standard one. So the most basic quadratic function is the parabola y equals x squared. Now, what I was saying yesterday was this. Why do we spend so much time on the linear function and the quadratic function? Because those two functions are the building blocks of every polynomial. Because all polynomials can be factorised down to be a combination of them. Now, just like the straight line, we can build any quadratic from y equals x squared. Again, via translations, rotations, reflections, or combination. We could get any other parabola. And if you needed to, well, if we recognise it, well, we know it's y equals ax squared plus bx plus c is our general one. So we're basically looking for, oh look, the dependent variables to the power of 1 there, and the independent variables to the power of 2. So we see one of them to the power of 1, one to the power of 2. We know we got a quadratic. Completing the square was a technique we saw with quadratic equations, and it comes in useful here too. Because my general quadratic, I could factorise to look something like this. A outside of x minus h squared plus k. Now when it's in that form, I can read off it the vertex straight away. I know the vertex of that would be hk. So if I complete the square on the quadratic, I can get that vertex straight away. A, of course, measures the concavity. So that's still the concavity. So there's the one we did yesterday, x squared plus 8x plus 12. So if I was to do it to this one, complete the square, now we know that when we complete the square, we will end up with x plus half the coefficient of x all squared. So for this one, I know I'll end up with x plus 4 all squared. But if I was to expand that out, I'm not going to get 12. I'll get 16. So therefore I need to subtract 4. So now I can read off that and get the vertex straight away. Look at the general form, x minus h. I've got x plus 4. Well, plus 4 is the same as saying minus 4. So I know the x value of the vertex is minus 4. K, that constant number, the y value of the vertex, that's also minus 4. So I've got it straight away, there it is. Vertex is minus 4, minus 4. That's all to do with the shifting idea, moving the parabola around the number plane, and we'll look more into shifting with all our functions later on. So the x-intercepts, well, seeing I've got it in completing the square form, I can use it that way as well. So I'll go x plus 4 squared minus 4 equals 0, because x-intercepts when y equals 0. So x plus 4 squared is 4. So x plus 4 is plus or minus 2, which gets us the 2 x-intercepts. We had a question, you'll remember. Write down the quadratic with roots 2, 8 and vertex 5, 3. So another way I could have approached this problem. I could have said, well, look, I know it's always going to be in that form, but I know the vertex. The vertex is 5, 3. So it must be in the form some constant times x minus 5 squared and then plus 3. Notice the constant is only times the square. It's not times the 3 as well. If I set it up like that, then I can substitute in any point I like to get what k is. So I've substituted in 2, 0. Oh yes, because that's one of the x-intercepts. So I've chosen to substitute in 2, 0. There we go. We end up with k equals minus a third. Minus a third. And so there it is in factorised form, well, sort of factorised form, completing the square form. If I expanded it out, we could see, oh look, we got the same equation that we saw yesterday. So that's another way of looking at quadratics, which might make questions easier. Here's another idea, this thing called the discriminants. Now the discriminants, the symbol for the discriminant is the Greek letter delta. It's not just a triangle, it's actually the Greek letter delta. And it's equal to b squared minus 4ac, that bit under the square root sign in the quadratic formula. The vertex, now we know the x value is the axis of symmetry, minus b on 2a. But I don't know whether you knew that the y value can be written as minus the discriminant over 4a. That's how you can find the y value straight away. And of course our x-intercepts, well, it's the quadratic formula. Minus b plus or minus the square root of, well, discriminant, b squared minus 4ac, all over 2a. Notes, it tells us some other information as well. If that delta, or discriminant, is less than 0, then there must be no x-intercepts, because we'd be saying the square root of a negative number. We can't find the square root of a negative number. So we get no x-intercepts. So we don't actually have to factorise the whole equation down. We can just look at this expression, b squared minus 4ac, to work out whether or not it has x-intercepts. If it turned out it was equal to 0, then we must be talking about a parabola that just touches the x-axis, because we only end up with one solution, because we'd be saying plus or minus the square root of 0. The square root of 0 is, of course, 0. And if it turns out to be a number bigger than 0, now we know it's going to have two solutions, because we'll have plus or minus the square root of whatever the discriminant happens to be. Let's go back to that same parabola again and how I would use this idea. So y equals x squared plus 8x plus 12. I'll work out the discriminant, so b squared minus 4ac. In this case, it's 16. So straight away now I know the vertex, minus b on 2a gets me minus 8 on 2. And then the y value minus the discriminant on 4a gives me minus 16 on 4. And there's my answer, minus 4, minus 4. Oh, before I move on to the next bit, where it's really useful is those questions which say find the maximum or the minimum value, because you don't actually need the axis of symmetry now. You can work out the maximum and minimum by just using minus the discriminant on 4a. You don't have to worry about finding the axis of symmetry, then substituting in to get the answer. So that can save a little bit of time. So all right, our discriminant basically tells us things about the roots. We just talked about how many x-intercepts, but it also will tell us whether we have rational or irrational roots. Right? So discriminant greater than 0, two different roots if it will cut the axis twice. That's what we just talked about. Discriminant equal to 0, it actually still has two roots. It's just that they're the same. Right? So you have two equal real roots, but it'll touch the x-axis once. And less than 0, no real roots, it still has two roots though. They're both imaginary. So every quadratic actually has two roots. Just sometimes they're real, sometimes they're imaginary, sometimes they're different, sometimes they're the same. But that one, of course, never touches the x-axis, because imaginary root, well, how on earth would you plot an imaginary number on a number plane? If it is a perfect square, well, then I know the roots are rational, because I can find the square root of a perfect square. And obviously, if it's not a perfect square, then they must be irrational. We'll end up with plus or minus the square root of something. So we're going to describe the roots of 2x squared plus 6x minus 3 equals 0. What are these roots? What do we know about them? We'll find the discriminant. It's 60. It's greater than 0, so straight away we know there's two of them. It's not a perfect square, so I know they're going to be irrational. So I've got two different, real, irrational roots. That pretty much covers everything. Find the values of k if this one has no real roots. So this is the situation where the roots are imaginary, but it'll be discriminants less than 0. So we know the unreal roots, or the imaginary roots, they're going to occur when the discriminant's less than 0. So the discriminant for this one would be minus 4 squared minus 4 times 2k. 16 minus 8k is less than 0, so k is greater than 2. So if k is greater than 2 in that expression, we know that quadratic will have no real roots. Ooh, there's a few questions there.